Okay, last lecture we introduced drag and the coefficient of drag. Continuing along and going into more detail into drag and calculations of drag, that's what this lecture is going to be about. So, drag and Reynolds number. We're going to look at the effects of Reynolds number on drag and coefficient of drag. Okay, again, the coefficient of drag is going to be determined experimentally. Forces are going to be measured, then the flow parameters will have to be quantified, and following the formula we went over last class, we can define the coefficient of drag for various shapes, profiles, and or objects that you have given in a particular flow field. Coefficient of drag is a dimensionless number. So we have to come up with these coefficients of drag for various Reynolds number where appropriate. And again, these non-dimensional numbers help when we have similitude and doing comparison from models, scaling up to real size prototypes, either larger or scaling down to build a prototype that's on a much smaller scale. These are going to be ways to come up with the experimentally defined coefficient of drag. However, there are theoretical or numeric or closed form solution to come up with these models, but we're going to go over those simple cases later on in the course. Okay, so what I want to cover right now is some experiments seen for a sphere. So a sphere is going to be represented like this, such as a baseball, golf ball, any kind of round object, basketball that you would have. So right now we're going to be focusing on the coefficient of drag for spherical objects. Okay, the results from experiments show that at Reynolds number on the order of magnitude of 10 to the 5th, the coefficient of drag decreases. If you remember from previous points in this course, what occurs when a Reynolds number gets to be about 10 to the order of magnitude 10 to the 5th? That's where you start transitioning in from laminar flow to turbulent flow. So, So again, this is going to be where our flow transitions from laminar, very, very smooth flow, to turbulent flow, very chaotic. Okay, the reason for this is the interplay between the equations that govern fluids, which is the conservation of mass, momentum, and energy. So as those need to be solved simultaneously, you're going to have different effects on the forces and the different coefficients that you have. So this is going to be beyond the scope of this class, going in the interplay of these equations. However, if that is something you would like to study, that would be a class in Computational Fluid Dynamics, or CFD, Computational Fluid Dynamics course. Take it, it's fun. So from the results from experimentation, throughout the note packet there's going to be, or throughout the notes for this lecture, there are numerous graphs. However, I'm only going to draw one of them. So if we have a graph, and we have Reynolds number. So here we have values of Reynolds number. Now in your homework assignments upcoming, if you notice the scale on the bottom, this is going to be representing a semi-log graph. Where this is going to be semi-log, the bottom is going to change by a factor of 10, and along the side, going to be your typical scale. That's going to be a semi-log graph. Also, for some of your homework assignments, it might be better served to plot things in a log graph. So after the first set of homework assignments that you have done in Unit 1, you should be familiar with using a spreadsheet program. In there will be a way to change the scale on your various graphs. That'll be an easy thing for you to do. You can Google search that, how to do that, in whatever program you're choosing, whatever version that you have. But visualizing the data might be more efficient to use a semi-log or a log-log or just a traditional graph. But you'll have to mess around and play with those, and whatever you see for those, the best way to illustrate the results, or best way to show the results. So for this one, it's a semi-log graph. So on this side is going to be the coefficient of drag. So what we can see is roughly going along something like that for the coefficient of drag for a sphere. Coefficient of drag varies as your Reynolds number varies. And again, a semi-log graph illustrates this phenomenon much more efficiently. Okay, so representing a shape that is similar to a sphere, but nothing like it, but is going to be a cylinder. A cylinder is going to be represented such as this. So if we have cases where we have flow in a sphere, here's the sphere, air would be blowing over top of it. It's going to be symmetrical in whatever direction that the air is blowing around it. If you have a cylinder, cylinder is going to be represented like this. So if you're going to have the flow going along this line, is going to be different than if the flow is going to this surface. Also in your notes are going to be Reynolds number for cylinders. Again, once you have this, you're going to have three-dimensional results that you'll have to do for your calculations and experiments to come up with a coefficient of drag for a cylinder. Alright, let's use this result for a sphere. Let's do an example problem. So let's calculate the drag, the force of drag, on a Alright, let's calculate the force of drag that's going to be seen on a sphere that has a diameter of 0.1 meters in a flow that's represented by a Reynolds number of 50. A density of the fluid, in this case air, is going to be 1.201 kilograms per meter cubed, and the viscosity is going to be 1.8 times 10 to the negative fifth pascals times a second. So remembering from our other class how we define the coefficient of drag, in this case the coefficient of drag has been given for various Reynolds numbers. So solving this now for the force of drag, which equals 1/2 the coefficient of drag, density, velocity squared, area. Now I have to go through and calculate or use what each one of these values are. So, substituting this in 1/2, the coefficient of drag. Okay, we haven't experimentally determined what the coefficient of drag is, but we have the results here. So looking at what about 50 is, reading from our scale, we're at a coefficient of drag of about 1.4.